All right, I think it is probably time to start. Welcome to this CySER seminar, the very last in the semester. And I know this is finals week, at least here at WSU. And we appreciate that you joined us. Happy Monday. Today we have the great pleasure of having Haipeng to speak to us. Haipeng is a colleague of mine here at WSU. He is a cybersecurity expert. He's an associate professor in our school, and his research generally lies in software systems and security, with a current focus on program analysis, assisted by machine learning methods to secure applications to things that are multilingual software, distributed systems, and mobile apps. His main goal is to develop practically scalable and cost-effective techniques and tools that improve the productivity of software developers and the quality of large-scale, complex, real-world software systems. I am stepping in for Noel Schulz, who could not be speaking today, introducing the speaker. You know how things would go. You can put in your questions on the chat window as Haipeng goes through, and he will save some 5-10 minutes towards the end for discussions. But today he will be giving us a manifesto, Sustainable Defense Against Evolving Malware in the Android ecosystem. So without any further ado, let me give the floor to Haipeng. Go ahead, Haipeng.
Okay. Yeah. Hi, everyone. Good afternoon. So thanks, Siva, for the introduction, and thanks to the CySER team for giving me this opportunity to take this opportunity to look at what our team has been doing in the past few years regarding what we call the sustainable defense. So I'm going to first clarify the context in which we are actually looking at all the problems related to malware detection and malware diagnosis. And the focus here is sustainability. So we will mainly talk about why sustainable defense is a must, and why it is challenging. And we are going to talk about the current results we have obtained, but also we'll be looking forward to some of the future challenges and potential, like envisioning some potential solutions. So Android, I think without much justification, so it's a pretty kind of popular kind of mobile platform. And in fact, so this diagram, unfortunately, so this organization has not continued to update this kind of statistics, but based on what they have done this like 2 or 3 years ago. So this is roughly the distribution of the market share of different mobile operating systems and surrounding it, the entire software ecosystem. So yeah, so I think you and I probably, if we are not having like very good affordability, maybe we are just using Android products. It's pretty cheap, and also it's pretty awesome in terms of functionalities and also in terms of how fast it's being maintained and updated to the latest kind of user requirements. And so this is the statistics from some online kind of like data collection kind of agencies. And this one is more like from the user's perspective, because if you think this one kind of providing in terms of the vendor's perspective, like how many like Android devices have been delivered, have been sold. But this one actually talks about how many operating systems are actually being used when user access all kinds of websites, because this is from the State Counter website, and this website is dedicated for providing a page tracking, page visit tracking kind of services. So basically, if you have a website and if you put a few like JavaScript code, and they will track how many users are actually accessing your website, those kind of things. And from here, you can also see the dominance is definitely very clear. And those are for the up to 2019. And the only other data I can find from online is this one. This is pretty latest. So actually compared to like 2 or 3 years ago, the dominance of Android only went up, as you can see. So this is the number for Android, and these are for the other two systems, including everything else, including Windows. So I think there's no doubt that Android is pretty popular. I think its dominance will continue to increase in the some foreseeable numbers. And one of the reasons that Android can be so successful, in my understanding, is because around the Android platform, it also has a very good user community, including the developers and, of course, you and I as users. And of course, the developers provide and the users are using a very tremendous number of applications which cover, according to the latest categorization of functionalities on the Google Play Store, it covers more than 15 different categories, like for kids, for different people of different age, at different level of ages, and also for different purposes for education, music, entertainment, almost everything. So you can always find an app to do something that you can think of that a computer would be able to do. So these three things, this is what, in my understanding, this kind of triangle formulation of the ecosystem, in my opinion, actually justifies why the Android world is so successful and popular. And of course, part of the reason that we want to look at this whole ecosystem is because, of course, in today's talk, I'm talking about the security. I'm talking about malware detection and malware diagnosis. So I think Android apps, I mean, these are relevant for a very clear reason, because we are actually looking at most of the time the malware among the Android apps. So we don't have much malware in the Android platform. So we actually have some vulnerabilities, but they are not malware. But why is this relevant, right? You may be asking, why the Android users become relevant regarding like the malicious behaviors of the applications? Well, the reason is because on the one hand, sometimes you can actually find a very clear connection between the user community and the apps being malicious. For example, if you look at the reputation of the developers on the one hand, or looking at the users' comments on the other hand, you can actually use those kind of information to formulate some kind of model to detect whether certain apps are malicious. For example, if most of the users are discussing about some potential malicious or suspicious behaviors of certain apps, like maybe some fake version of TripAdvisor, or like some kind of camouflage kind of malware detector. So they claim they are detecting malware, but actually themselves are actually malware. So if the users actually pinpoint those kind of things on the user feedback forum, just like Google Play Store, you can find a lot of user comments, and from those information, you can also identify some good hint about potential malware behaviors. On the other hand, if you see that app developers, some certain app developers have a long history of being notorious in terms of providing a malware, and in the next release of that developer, you want to be probably more like cautious, because this guy has been doing malware development for all the time. So maybe the next one is probably likely another malware. And this ecosystem, of course, fostered the success of Android, but also at the same time, it also caused some trouble from a security defense perspective. The main reason is because this ecosystem, not only the Android apps, but also the entire ecosystem actually moved very rapidly and constantly. So to provide some quick, kind of perception on that, so this picture shows only up to 2015. I did not get these kind of nice pictures that are capturing the entire evolution history, but basically you can assume that it basically continued at this kind of pace. Almost every year, at least one more version of the Android platform is released. So right now is, if I remember correctly, right now Android is at version 9 or 10. But only 2 years ago, it was only Android 6. So you can see how fast it goes. And so on this kind of a timeline, each point represents one of the major releases of Android platform. So this is not the Android applications. This is the platforms, the operating system and the development framework, and including also the customized kernel version for the Android OS. So this is platform evolving. And the implication of this is that every time when the platform evolves, the developers have to adapt to that evolution. For example, every time a new Android platform is released, they will basically release a bunch of new Android SDK APIs, the software development kit APIs. And because Android applications are just like one of those kind of framework, heavily framework-based application development, which means most of the time, if you want to create a new app, the developer usually only write very little code. And most of the code are already provided by the platform. And Android already has a very rich set of functionalities implemented through APIs for managing the hardware, for managing some of the even common level kind of application framework level kind of functionalities. For example, to query whether the battery is running out. If the battery is running out, then my application need to give some kind of warning to the user saying that, okay, you need to save your stuff, and because the phone is running out. So those kind of things. So those like common basic functionalities are all provided in a very rich manner by the Android platform. So the user only needs to write a very small portion of the code for any given new application. And the problem that this actually causes is that you can have at least the two major issues. So the first issue is that this diagram shows one of the state-of-the-art malware detector and how it performs over time. So the x-axis shows the time span. What that means is this particular detector, just like many other detectors these days, are based on machine learning. So yeah, because it's popular, right? Everybody wants to try using data-driven approach because it avoids many other issues. Potentially it can be more generalizable than a deterministic approach. Because if you think about a deterministic approach, you have to define all these kinds of rules, and those rules have to be engineered by humans. So relatively learning-based approach is relatively more kind of generalizable, because if you want to adapt to a new kind of population of apps, the worst thing at least that you can do is that you can just retrain the model. But I will get back to that same issue. So that actually is one of the major issues I want to cover today to motivate sustainable defense. So this y x-axis shows the number of years since the model was trained, and until the model is retrained, basically. So let's say you train the model on 2010 applications, and then after 1 year, you want to use the same model without any change of the model, without any retraining. You apply the model to the applications that were developed in 2011. So that's like 1 year later. So as you can see, 1 year later is still pretty good, right? You get 92% accuracy in terms of this kind of binary classification, like just telling me yes or no, whether this is benign or malicious. And only after another year, you can see a big drop, like more than another big drop of this. So so this is another, so this is 1 year, right? And if you continue to look at up to 5 years, the model becomes almost useless. So it's not even as good as a random guess. Of course, we are talking about in a intuitive manner. Sometimes, getting 100%, getting 50% accuracy is not something that you can take for granted. If you are really actually doing this kind of detection, like throwing a dice, it's not going to give you actually 50%. Yeah, but we are actually talking about in a intuitive manner. So, basically, this kind of model deterioration problem is one of the emerging issues in the community of malware, of mobile malware particularly. So why so special with like the malware being mobile? Because mobile ecosystem is the most thriving, most vibrant software ecosystems among all different software applications. Part of the reason is because people have the easiest access to mobile devices. So ordinary people are not using standard computing platforms like desktop computers or workstations, not to mention like those like high-end servers or maybe clusters. Those things are not even particularly feasible to ordinary users. They're maybe not even aware of those kind of systems. So to most people, computers are basically mobile devices, or even more particularly mobile phones. So it's malicious software domain. So yeah, so this kind of problem is demonstrated in this quick deterioration of Android malware detection. But another issue is it also causes tremendous compatibility issues because the platform keeps evolving, and application developers may not be really keeping the pace very well with the platform providers. So oftentimes they have some kind of miscommunication, or maybe the documentation sometimes is not entirely, without confusions or inclarity. So because of that, developers usually use APIs that have already been outdated, or the hardware platform does not even support those kind of APIs anymore. And when the applications using those APIs are running on those kind of hardware platform, the application will crash. So that's what we call the compatibility issues. But today I'm not going to talk about compatibility issues. We mainly look at the malware detection problems. And malware is also, likes very much Android platform. Again, the reason is because Android is so popular. So from the malware developer's perspective, of course, that's the best way to make the big impact of their malicious attacks, right? So if you have a certain kind of well-engineered, well-crafted malicious apps, you want to make the biggest impact in terms of getting some profits, or just maybe sometimes just for like some other evil purposes. You want to have the biggest impact, then you should target Android, because Android is the most prevalent platform. And I have said this kind of interesting statistics I collected actually just 2 days ago. If you search Android malware detection on Google Scholar, only within this year you got this 3,000 results. Of course, some of these are noise because Google Scholar isn't perfect, but you can actually I think it's pretty reasonable to estimate that probably 1,000 papers, at least 1,000 papers coming out in this year alone. Like since 2000, I mean, we are now just in the first half of December. We are not even yet finished this year yet, but basically in the first 11 months, we already have 1,000 papers on Android malware detection. But ironically, on the other hand, so given this tremendous investment of the research community on this problem, Android malware only keeps increasing. So this number only shows like 2019, but I can very confidently share with you that this number only gets worse now. It's not getting any better, even though I don't have this kind of nicely depicted kind of figure already provided by some authoritative sources. So this is the latest figure I can get from the most authoritative source. And and this is also one of the favorite topic, in the presentations given by the Apple executives, right? So Tim Cook was talking about this, I think, 2018, when he was basically covering the security concerns with the Apple, with the iOS ecosystems. And this diagram shows like among all the mobile malware, 99.9% can be blamed with Android. So Android is the main problem. So and actually probably that's true. So some of our audience probably are using Apple products. You will experience less trouble with malware attacks. And this figure also shows, kind of in accordance with my previous figure, previous like summary about the compatibility issues. We actually did our study in 2019. Over the years, from 2010 to 2019, even among the benign apps, the compatibility issues are also arising. Yeah. So, but this is like more like a side kind of background. Basically, I'm trying to say, the deterioration of technical defenses or any other like app analysis tools have become a very problematic, kind of challenge in this for this Android ecosystem. And I want to make this, people are still using like precision recall or like cost effectiveness as a major metrics for measuring a technical approach for Android security or maybe just for the mobile security at large. But I would argue that sustainability is becoming a more like, prominent issue in this kind of, technical defense landscape. And the manifesto I want to make is, I believe any defense solution, especially those against mobile malware, should sustain. So you can maybe get certain kind of capabilities, like you can detect all different kinds of malware, like in terms of, how many different kinds of malware families you can actually detect, or how awesome your detection may be in terms of like high detection accuracy, like 99%. I mean, but how long you can sustain that kind of capabilities and that performance over time without frequent updating or maintenance? So why does this matter? Why do we care so much about not being able to frequently updating or maintaining your technical defenses? I think so. At least 2 points. First thing is, especially for learning-based approaches, we are not talking about like rule-based approach, because rule-based approaches are even worse in terms of sustainability, especially in this kind of Android world where everything is moving so fast, and you don't have that kind of manpower and manual efforts to keep to keep pace with this kind of fast evolution. But even with automated learning based approaches, the problem that you may not be able to, frequently updating or maintaining your model is because, first thing, usually this model must be trained on a huge amount of training samples in order to be effective. And the training on those kind of huge amount of data set, of course, takes a lot of time. For example, some large models, I'm not sure whether this is perfectly fair to make this kind of comparison. But if you look at some of the large language models today, for example, recently, ChatGPT is gaining a lot of attention. But if you look at how long this model, has taken for training, you probably understand why I'm actually raising this issue here. It usually takes probably several weeks, if not months, to train the model in order to make it really, powerful. So overhead is one issue. But I would argue a more critical issue is you lose their ability to actually defend against 0 days. You won't be able to have the ability of training samples for you to update the model. So for example, if you want to detect a new emerging kind of malware, and you got to have these training samples to train the model on those kind of samples in order to detect those kind of malware. But as soon as you got those samples and you're able to detect them, it's already too late. I mean, it's not 0 day anymore. It's probably 1 day, 2 day, or even 10-day malware. And during those 10 days, you don't know how many evil things those cyber adversaries can do. And they can exploit whatever kind of weaknesses you have by running their malware in your space, in your cyberspace, and basically damage a lot of kind of facilities you may have. Right. So yeah, you don't have the ability, you don't have the availability of the samples to retrain. It's not because you don't want to do that. You cannot do it. It's not feasible. And because you cannot do that, then your model will suffer from the inability to detect 0 days. So what should we do about it, right? So we need to come up with some better solutions. We should stop like keeping like the endless game of coming up with new features and finding new ways to to engineer like new features to develop new machine learning models, but not addressing this fundamental issue. I mean, if you're developing a new malware detector, I'm actually not going to be a big fan of any like advanced like using any most recent advanced kind of learning technique, a transformer, like graph neural networks, whatever. So if you're not addressing this issue, I mean, you are still leaving bigger room for cyber attackers to leverage this kind of, sustainability insufficiency of technical defenses to continue to make damage security-wise. So I believe we should definitely embrace the evolution, even though we know evolution is the cause. And by the way, here when I say evolution, I'm actually talking about two issues that can be categorized as being caused by evolution. One is the natural evolution of applications because of the keep changing user requirements, because users are asking more and more with all the user application context changes. For example, many of the social kind of cultural kind of factors are changing, and the user also are asking updates of the features. So the applications need to evolve in order to be successful. So that's like one of the major principles of software engineering in general. So that's what we call the natural evolution. Another kind of evolution is out of malicious purpose. So we call those adversarial evolution or adversarial evasion. So basically, the malicious parties are purposely making some noise into the applications and make them look very different and behave differently from the normal. Sorry. Oh, okay. Yeah, no question, right? Okay. So basically, we have this kind of huge issue, with not being able to sustain their ability of detecting malware or diagnosing the cause of malicious behaviors. So and what I'm proposing is two approaches. One is we need to do a systematic categorization to understand how the ecosystem entirely behaves. So in particular, the relationships between applications evolution and Android platforms evolution, and also how the user community has been evolving. So looking at this in a systematic way and correlated way. And another solution is we need to keep mining this kind of data set from the ecosystem in order to make sure that you always have the most updated kind of training data set to maintain your model. So you may be saying, okay, you just said you don't want to do frequent updating. Of course, yeah, you should not do very frequent updating, but you cannot totally avoid updating because you won't be able to develop a sustainable decision, a sustainable defense that will sustain forever, right? You can only you can only slow down the deterioration, but you cannot totally, avoid that. But what we can do is that we can do this kind of, sustainable defense based on systematic categorization or continuous mining of the ecosystem. And this is a high-level idea. I think probably we probably don't want to get into those low-level details. But the high-level idea is that on the one hand, we are running continuous ecosystem data mining to search. We are following a system kind of approach. We have a database to maintain and keep crawling all these kind of ecosystem data, including the Android application data from the Android repository and the Android platform data from the Android repository and the user applications from app stores, and also the user community data, like the user reviews or developers ratings, those kind of information from the Android markets. We are crawling those data and establishing some kind of quick indexing approaches to facilitate search and storage and efficient storage. And once so on the one hand, those data are keep getting into the database or maintaining the database. And so you are going to get all this kind of updated information about the ecosystem stored in the database. And simultaneously, we are running what we call this systematic evolutionary categorization. And these categorizations are backed by some of the application analysis, including system level and application level code analysis or non-code artifact analysis, and even including some natural language processing techniques to process the user community data, and using some text mining data kind of techniques to process any non-code artifacts that are textual. And we are taking this kind of user community data from retrieved from the database, and platform information are also some of the applications, and we are providing the query interface in order to more efficiently to get the data out of the database and then conduct all these kind of analysis, and we put the results back into the database. And from this kind of results, we have another level of querying interface to quickly query those like analysis capabilities to retrieve, for example, what are the current patterns of the user applications leaking, for example, the SIM card ID, things like that, or any like malicious short message services, kind of those kind of malicious behaviors. If you want to query those particular kinds of malicious malware behavior patterns, we provide that kind of a query interface. And based on this query interface, we can build a sustainable application. So why this can be more sustainable? And so as I clarified earlier, the reason is because you get all the updated kind of knowledge about the ecosystem, and you know what is actually changing. And this kind of information automatically kind of computed and stored in this database. And you can query those kind of latest feature, and then you can develop learning-based approaches or even rule-based approaches. If those rule bases are not heavily relying on human effort, by utilizing all the latest insights about the ecosystem. So that's basically a very, very high level kind of understanding of how this architecture works. And we can also provide, on the other hand, so this is like more like a reactive approach. Which is you develop the application detection, malware detection approaches based on those latest, insights about ecosystem. But on the other hand, we can also provide some proactive approach, which is based on this kind of querying capability. We can also, model what is good, what is actually what meets the high quality standards for the applications. And in terms of what we call the health profiling, which basically we can establish what we call the health profile of Android applications, or in other words, what developers should do in order to make the applications more secure and less vulnerable. So we can provide those kind of things to app developers so that they can actually build the first line of defense, even during the building process, even during the development process of applications. And that's the running component works. So I probably want to skip this one and also this one. So basically, this is like more like a zoom in of one of the modules in the previous architecture diagram. And in the categorization module, we want to categorize each of these three separate kind of kinds of data. But more importantly, what I want to emphasize is we want to actually compute the relationships among those three kinds of data. For example, how the app behaviors changes are actually correlated with the platform category, platform kind of information. So why does that matter? Well, the reason is because usually the app behaviors are very closely tied with the platform features, such as permission mechanism provided by the platform and the APIs, the latest set of APIs provided by the platform. Because as I mentioned earlier, application code is like a very small, tiny bit of the entire application. Most of the things are provided by the API in the SDK of Android platform. And the user dynamics and developer dynamics are also very important because security ultimately is largely about humans. It's about human factors. That's also why so many recent security studies are actually focused on how humans' decisions are affecting the overall cybersecurity space, this security of the whole cyberspace. So I think this is like the high level kind of overview of how we can actually make these defenses more sustainable. And because in the interest of time, I think I would probably want to get into one of the concrete technique for sustainable defense, which follows the methodology I just overviewed. And in this particular instance, I'm going to talk about two pieces of concrete technique. First one is the evolutionary categorization study we have conducted in the past 2 years, and we are trying to find how the behavior of malware versus benign applications evolved over a decade, over a long time of of history, and we are also using what we found out from that study and building a more sustainable Android malware detector. And finally, I'm going to actually share some, insights about why our approach can work better than the pure techniques. So there's a very, very urgent need to understand how the malicious behaviors versus benign application behaviors have evolved over time. Because if you don't understand these kind of evolutionary differences, you won't be able to sustainably differentiate Android malware and benign applications. So we are conducting this study by looking at a huge amount of it's not like tremendously huge number of applications, but a relatively large kind of data set. And we look at those data set over 8 years span. And we have 15,000 benign apps, 15,000 malware. And we look at, and these applications are gathered from a range of Android markets, including the official markets Play Store, but also some other third-party markets. And what we do is that we are running these applications against automatically generated inputs using the Monkey tool. So Monkey is provided by Google for like the basic testing of Android applications. So what Monkey does is that this tool generates all the different possible operations on top of the GUI, on top of the user interface of applications, and trying to trigger as diverse a set of behaviors of applications as possible. And what we do is that we keep providing each application for 10 minutes, and we aimed at 60 to 100% coverage. And the median coverage we have is almost 75%. This is actually a big deal because you cover most of the code. Even though, code coverage doesn't mean you actually exercise all the behavior, because here we are talking about the 9 coverage. We are not talking about the program path coverage. So 9 coverage is a relatively weak kind of coverage criterion, but this is basically what we can do with the best that we have. And even by just doing this, we spend a year to provide, to run these applications, each one for 10 minutes. Because oftentimes when you run a certain application, maybe the emulator crashes and you have to restart. Because the randomly generated test inputs can be quickly, can be easily become malformed kind of inputs, which can crash the applications often, very often. And we got a lot of dynamic traces, and based on the trace, what we did is that we categorize how malware over the years, how malware behaves versus how benign apps behaves in terms of some code level structural behavioral patterns. For example, we look at how different code layers are interacting inside the application code. For example, user level code and the platform code, how they are interacting in terms of the number of function calls between those 2 layers over all the function calls that are happening in the application execution. So you can see a clear difference over time. Even at any point, you can see a clear difference, but over time, the trend is also different. For example, in terms of commonalities, benign applications and the malware, they both have decreased the cost to user application code. I mean, that's basically our kind of a signaling, these kind of increasing, small portion of user code in applications, as I mentioned briefly before. So basically, Android applications are increasingly developed with, decreasing user code. And on the other hand, we can also see that malware had much more cost to SDKs. So this is this is the malware's behavior. If you look at all the cost to the SDK, from SDK to third party. So this is the SDK code to third party. So that's represented by red. But the benign applications actually has more such costs within the Android framework, which is SDK to SDK. So this is the SDK to SDK, which means benign applications should increasingly rely on what should be handled by the platform itself. And this kind of trend is also increasing. This actually points out to some of the challenges we just mentioned earlier. You can see up to some later years, if you look at the sheer distribution of the SDK to SDK calls, they're actually getting pretty similar, getting pretty close to the benign apps. That makes also the Android malware detection based on these kind of features very difficult. But earlier years, yes, it looks very good, right? If you build your application, like you build a machine learning classifier based on some of these kind of function call percentages, you can actually get a pretty good performance, because they are very different, right? You look at this, the SDK to SDK up to 2015, they are very dramatically different, but later it's less different. So on the one hand, we can see this kind of difference between malware and the benign apps over time, but also this also kind of signal the challenge of sustainable defense. But on the other hand, we also found some exciting results, and this one shows part of that. So for some of the particular features, for example, the call site that targeting a particular information sink, and also the call site that targeting all the calls that targeting a vulnerable information sink. So these are two different things. Call site are counted by how many unique calls you have made in the code, but calls here are counting all the instances of the calls. So, but regardless, in both kind of perspective, you have very clear differentiation between benign and malware, even though their gaps are not always consistent. But at least there is one thing that is consistent, which is you never have this kind of dramatically exchange of the patterns between these two groups of apps. What I mean is, for example, in terms of this kind of particular feature, so the benign apps is always above. So for any given year, is always above the malware's statistics in that regard. And on the other hand, in terms of this feature, it is exactly the opposite. The malware is always above the benign for any given year. Sometimes the gap is really kind of very thin. It's very hard to differentiate, but still, it's never get like they swapped entirely. Like maybe you jump up and the other one jump down and they got across. I mean, because for learning-based approaches, what we need to do is that we want to find this kind of what we call decision boundary. If the decision boundary is easier to find, then of course the model will work better. If you have this kind of winding around kind of or like interleaving kind of curves, then intuitively you can see to find a decision boundary for that kind of situation is much more challenging, right? So what we do is that we will take advantage of this finding and use such features basically derived from this kind of evolution study and use these features to come up with a new learning-based approach. So this is all about like we we carefully select the features that can sustain over these kind of features that can constantly differentiate malware behavior and benign application behaviors. And use this model, we came up with this kind of technique called droid span. So I think in the interest of time, I probably want to skip the technical details here and just jump to some of the key results. So, and this is the most interesting results here. In terms of, okay, let me see. In terms of sustainability. So we define sustainability by two metrics. One is reusability, which basically means without retraining, how long the model can sustain. And the other one is if I do some kind of retraining, oh, I think it's the opposite. So reusability is that if I don't do the retraining, then how long you can sustain. And sustainability basically says if you don't retrain the model, then how long you can sustain. And so this curve clearly shows the big advantage of droid span over 5 state-of-the-art malware detectors. So basically, our technique can sustain almost like around 80%, sometimes go up to almost 85% accuracy, even with a very long gap of 7 years, which means the model was trained on 2010, and without any change, until 2017, we can still capture 85% of the malware that came out in 2017. So this is a big advance. However, there are still many remaining challenges. Yeah, so I want to leave a couple minutes for questions. So let me wrap up this quickly. So we can develop a sustainable defense, but it's not going to sustain forever. We still need to somehow retrain the model at some point. But we want to slow down. We want to delay the retraining, because the longer you can delay, the more chances you have to capture what we call the zero-day vulnerabilities, the zero-day malware, not vulnerabilities. And so, so that's one of the remaining challenge, which is you can only mitigate the problem, but you cannot entirely solve the problem. And the other challenge is sometimes even short-term solutions can still be very challenging to develop. One thing is because I think I mentioned these two things earlier. You have two things going on in this space that make this sustainable defense very difficult. So applications, they naturally evolve. And also there are always some adversarial attackers. They purposely, craft their applications to make them evade the detection. So these two things together actually aggravate the challenge. And the future solution, on the one hand, we can improve the model design. We can use some more generalizable kind of learning approaches to make the model potentially more sustainable. So some of the models, by nature, they have better, generalizability than other models, especially if you use deep semantic features. So features that actually capture the application behaviors rather than looking at some, surface level, like superficial syntactic features, because those features can be very easily, changed. But semantically, the change will be smaller, right? So that's like intuitive idea. In terms of regarding the model design. On the other hand, we can actually generate data ahead of time. So even though we are not able to get the access to the emerging malware samples, because once you got them, it's already too late. You already missed the opportunity to detect them in a zero-day manner. But we can potentially capture how malware evolved in the past, and then trying to emulate how that evolution pattern can possibly continue, right? If you capture that kind of dynamic, you can actually generate new malware samples following that kind of evolution pattern into the future and use those generated samples to enhance your model, right? So ethical generation, we are not going to deploy those malware to cause any damage. We only develop these kind of samples to improve the model. And this will not solve the entire problem, but it will slow down the deterioration of the defense. Okay, I'm sorry that I'm not leaving a lot of time for questions, but basically, so and in this space, because this is one of the standing challenges in malware defense in the space against defending malware, especially in the mobile world. Yeah. Okay. Thanks everybody for the attention, and thanks again for this opportunity for me to share our recent work in this space. And let me see how much questions
Sure.
I can actually answer.
Yeah, thank you very much, Haipeng. That was a very
for
interesting talk.
making this a little
And
longer.
thanks everybody for coming on a finals week. This time, I know some of you might even have had exams, so we could have a couple minutes for questions, right? And please go ahead and unmute yourself or write in the chat. But there were a couple questions, Haipeng, that came around while you were speaking. And if you hear some voice that says exiting, that means people are leaving, and then don't worry about that. But there were a couple questions, and I think one of them was Nathan's question, who was asking, at the point when you were talking about certain things, he thought it was concept drift, and I think you would probably agree that was what was happening. But he had a question about your data set, whether that was, did you create your data set, and what were the most important features? If you could quickly answer that.
Yeah, thanks for that question. Of course, that's a very important question, because for learning-based approaches, data set is the key. So we actually did not create the data set ourselves. We are basically crawlers. So we kind of use this kind of crawler to automatically crawl the data from all the open sources, including the app repository, the Android, because Android is open source project. We crawl the open source versions of the Android projects called AOSP, the Android Open Source Project. And for user community data, they are also open source. They are also like generally public, available. So you can find them from Google Play Store or any other like third party. So and what are the most important features? Oh, okay. So the features we are using, we sustainably differentiate malware from benign applications, as I showed before. In those two plots, I showed some of the features. For example, in terms of the percentage of call site to sink, to information sink, or the percentage of call instances to some vulnerable sink. Mm-hmm. So in terms of these kind of features, so basically the idea is that we derive these kind of features that do not change in terms of like differentiating malware and benign over time. And we derive these kind of features through the evolution study, and then we build the learning-based approach using those features. Yeah, this is still not a very ideal kind of solution, but it works a little better than existing approaches. But in the long term, we should not be satisfied with this kind of approach. Yeah. So yeah, so let me see.
The other question was Adam's question. He asked if does Android develop faster than other cell phone operating systems?
Sorry, can you repeat? I think that's not in the chat, right?
It is in the chat. Does Android develop faster than other cell phone operating systems? I think, or by develop.
Okay, I saw that. Yes. Does Android develop faster than? Oh, yeah, I think so. Yeah. So Android, I mean, because Android has this kind of driving force of moving faster, right? Because it has much larger user community, and it has much higher demand for moving faster. So I guess that's yeah. I don't have the like very official study data to show that, but my impression is, of course, Android moves much faster. So if you look at how many versions, how many official major versions Google has released for Android platform in only like a matter of like 8 years or 10 years, and compared to how fast the iOS has moved, I believe Android is much faster. Yeah.
Well, one of the other things on the chat is just for people to remember to fill in the survey. That's for evaluation. That's important for the program. Our funders would like to know about it. So please do make sure to take that quick one after the seminar is over. So we are a little over time. I don't know if there is anything you would like to say, Bernie. Otherwise, I would like to wrap up here.
Yeah, nice job, Haipeng. You always do a great job, and appreciate all the information. And thank you.
Right. So we are past. We really appreciate your coming in today on a finals week, and thank you again very much, Haipeng, for a very interesting talk. And the material will be available after we'll get a chance to get the recording and the slides. This will be the finals seminar for this year. We will start again in January when the semester begins, and we will have a series of speakers again on the same day and bi-weekly. So until then, wish you well, and everybody have a great holidays ahead of you, and we'll see you next year.
Yeah, thanks everyone again.
All right, thanks
for
attending,
and good luck with your finals. Yeah. Okay. Yeah.
All right. Bye bye.
Bye bye. Bye bye.